So this video is supposed to follow our earlier discussion about work and how it relates to energy, specifically kinetic energy, as well as to the rate at which the work is done, that is power. We remember that work is a way of changing something's energy by exerting a force on the thing over a distance in the same direction the force is acting. And if you do that to an object to speed it up, then you're changing the object's kinetic energy. Now, we started out the previous video, we took a look at this football here, and we dropped it from a couple of different heights. And its end state, when it reached the ground, had different characters. It had a higher speed when it was dropped from a higher height, and gravity was allowed to do work on it over a longer distance. Same force, longer distance, did more work. Changed the kinetic energy more. But there's a way in which we can look at the work done by forces like gravity, where the work done depends upon the position between the objects. In this case, the difference between the position of the center of mass of this football and the center of mass of the Earth. Or, if we care more locally, say the floor of my dining room. One way to look at this is we could say, all right, I want to lift the football, or an example I've drawn here, we're going to lift a textbook, and when I'm holding on to the textbook, we've got weight downward, force of gravity downward, normal force upward. And I'm going to move it from here at about 1.2 meters to up here at about 2 meters. And there's a difference in what will follow when I release the book from those two positions. I release it from here at around 1.2 meters, and it hits the floor with some speed. And then I release it from 2 meters, it hits the floor with a significantly faster speed. Higher change in kinetic energy. So, one way to take a look at this here, we have on the book, we have our forces, the normal force up, the weight down. We start at rest, and we end at rest. So even though we sped up to get it moving, and we had to slow down to get it to stop, so our average acceleration winds up being 0, which makes our net force on it 0. And so that means when we play with Newton's second law of motion, the average normal force, the average force that I was exerting on the book, rather than the Earth, is the same as the book's weight. Also, we're moving the book up, the distance over which I'm applying that force. That distance is the same as the difference in the heights at the between the end height and the beginning height. So now we can take a look and see how does that play into the work that we've done on this while there was no change in speed. Before we were exerting a force on it to change the thing's speed, well, here I'm exerting a force on it. We're ignoring the force done by gravity, because we add those two together, then there's no work and no change in kinetic energy. Well, here we're just looking at the work supplied from the outside, but not through gravity. Then that same work is equal to the weight the normal force, times that difference in height. We distribute that mg, and we see we've got two terms again. The difference between some final state and some original state. And we're going to give those things a name. And I've labeled them already as PE final and PE original. What we're going to call those quantities, that MGH, not Mass General Hospital, it is rather the potential energy, in this case the gravitational potential energy. So potential energy, we're going to say, is the energy stored or increased by doing work against a conservative force. We got to define what the conservative force is too. So there's our definition. In this case, the force is gravity. So energy stored by doing work against a conservative force. And what that potential energy, gravitational potential energy, is when we have a constant g near the surface of the Earth is equal to mgh. So I threw in another term there, conservative force. And a conservative force in this case is a physics term, it has nothing to do with government. Instead, it means a force whose size or rather whose work, let's say, changes only with position. That is, only the starting point and the ending point matter for figuring out how much work was done. The path to go from here to there doesn't matter. It stays the same. We can say that it's path independent. So we saw there that the work that we did, the work that we do on a thing, can change its potential energy, like we did just now. Or, as in the previous example, it can change the kinetic energy. And that equation, we're going to go ahead and give a name. We'll call that, well, actually, we'll hold off the names for that. Before we added potential energy, they called that the work kinetic energy theorem, but not going to worry too much about that. What this does look like, it looks like something that we've seen before in our previous unit. We had a thing where we had force not times distance, but times the time over which that force acted. And that also changed some fundamental quantity. We had impulse, which was the net average force times the time over which that force acted, and it could change a thing's momentum. And we saw that these were true in open systems. In open systems, you can have an outside force, and that can change something's momentum through impulse, or it can change something's energy, and it can change something's energy through work. It'll do both at the same time. And so, just like with momentum, when we look at a closed system where there's no interference from the outside, then we have conservation laws. In closed systems, total impulse was 0, and so the total change in momentum was 0. But it's also true that in a closed system, our total work gets to be 0. I'm going to add some qualifiers to that in a bit. And so the total change in energy is 0. And so, just like with momentum, if there's no outside for the momentum to come from or go, momentum is conserved. If there's no outside for the work to come from or go to, then energy is conserved. Now, I said I was going to amend this a little bit. There's another method we have for transferring energy, which we're going to explore in the next unit. Energy can be transferred through differences in temperature or state of matter. And that transfer we call heat. So in a closed system, the heat and the work add together to equal 0. Let's take a look at a little demo here. down this goes. And over you go. Let's see. Well, I'll try. This will work. Okay, so let's get you on camera. All right, so here I have a little pendulum, and it's a certain height off the ground, and I can lift it up like so. Let's see if we can frame this a little bit better. Let's see, we go all the way out here, and then we go all the way out here. Okay, so let's call that good. All right, so I can exert a force on it against gravity. I can change its height, give it potential energy. And for the most part, the pendulum is more or less a closed system. We've got air in here, so that will make it open. But when we were first looking at this, we'll say that it's closed. And I gotta get my aim right here. So let's see how well this goes. So I can let go of it, and it'll swing back and forth. And at its lowest point here, it has lost the most potential energy, but it's going the fastest. And then at the points where it turns around on the sides, it is going to have 0 speed and 0 kinetic energy. So we have this going from having a lot of potential energy and no kinetic energy to when it's at the bottom going fastest, having very little, having the lowest amount of potential energy it gets, and maximum speed, maximum kinetic energy. It's continually changing from potential to kinetic. And it's not that it's instantly going from one all in one to all in the other. It's that it's gradually changing through the path. If you have like potential energy here and kinetic energy here at the beginning, as it moves, they're sloshing back and forth. So that when you add the total of them together, they're the same. The total energy stays the same. But wait. When we actually look at this, it's not quite what's happening. I let go, and it goes back and forth and back and forth. And I don't have to let it go too long, and we see that it's not getting as high as it was when I started. And yet, it had 0 kinetic energy at the turnaround point. But it had less potential energy than it started. That potential energy had to go somewhere. Where to go? Well, I said the air might be interfering. But does that mean the air is moving faster now? Or got lifted up higher? Well, sort of. There's not a breeze in here, really. But all the particles in the air that it's interacting with, and the particles in the pendulum itself, and in the whole structure to some extent, they all heat up a little bit. They all vibrate a little faster as this interaction continues. The kinetic energy, the average kinetic energy in all the interacting particles, the vibrational energy, that's increasing. The temperature is increasing. The total energy is not going anywhere. It's just changing forms from one to the other. Potential to kinetic to potential to kinetic to potential as we swing back and forth. But also, more and more is getting dumped into thermal energy, internal energy in all the interacting parts. This is one of our fundamental laws of how temperature flows, thermodynamics, that whenever we have an energy transfer or transformation that involves more than just a couple particles, some of that energy goes into changing the temperatures, evening out the temperatures, making the temperatures get closer to the average temperature of everything involved. This is one of the things that makes it so that you can't run chemical reactions backwards without dumping more energy in. We can burn gasoline and then take all the steam and the soot and the carbon dioxide and carbon monoxide that gets produced from that, and we put it in the right conditions to get a reaction going again. We can make octane from that. But in order to do that, we're going to have to dump more energy in, because some of the old energy that was holding it together as gas had been turned into thermal energy. This is what makes non-renewable fuels non-renewable. And that's where we're going to leave it for now.